biological dynamics are non-linear. They're what? They're curvilinear. They are curves. And therefore, mathematics, calculus in particular, does a very good job of modeling biological dynamics because it measures attributes of curves. So here's like a typical example of something like this, right? Find something to throw in. So I have something like this, yes? And I throw it in the air. Take a look at the graphic on the right there. So I go like this, and that's what it gave me, was a curve that looked like that, right? So by understanding calculus, I can predict with perfect accuracy how far that thing's going to go, how high it's going to get, where it's going to land, and how fast it's going to go. If I know how much force was required to do it, right? What was my initial velocity? I know what the gravitational forces are, and I know what the air resistance is. And as long as those things hold stable, I can predict that with actually every single time. Okay, so that's what it's basically doing. So just to kind of run through that again. As that little piece went up, if it was balls, the typical way this demonstration is done in physics, right? As the ball goes up, what happens to its velocity? It decreases. Why? Gravity's pulling it down and air resistance is slowing it down. Okay? So it gets to the point of the apex of the curve and it literally stops for a second, right? For a milli-minute second it stops. And then what does it do? It starts to go down its downward trajectory. And then it's going to increase the velocity due to gravitational forces and is slowed by air resistance. Okay? So it's going to be telling me that trajectory all along the line. Populations grow like that. They go up, they go down, typically in curvilinear responses. So when we think about this, this is highly useful for us. If you had the ability to calculate these things in your head instantaneously, like for instance, if you were a batter at the plate for baseball, and you knew what the velocity was being released, right? And you knew all these other patterns about the air, the velocity, and how it was released, and what angle it was released at, you would know exactly where the ball was going to be on the plate when it got to you every single time, which means you'd be the best baseball player in the entire world. You'd know, no matter how fast it was pitched, where it was going to go, all the spin, it wouldn't matter, you'd know exactly where it was going to be. That'd be pretty impressive, yeah? So that's what it's giving us the ability to do, is to predict into the future what biological dynamics are going to do for population size, right? So for a biological population, we can use these differential calculus equations to predict the population size at any point in time if we know the initial population size and the rate of population growth. Now this is not a class in calculus. So calculus is basically taking lots of short intervals that we can calculate easily and then adding them all up to create these curves, telling us what's above, below, and the curve itself. We're not going to do that. We're going to take a look at each of those individual segments and calculate one segment at a time. And so we're going to keep it simple, just so we can understand how to use the tool. So I'm going to start off with the simplest model here. And so in this model we have n sub t as a function of n naught plus b minus d plus I minus e. Well, what does that mean? Again, it's just symbolic language, so we walk through it. N sub t is the number of individuals in a population at any given time t. We look at n naught, and that's the number of individuals at the starting point, right? Times 0. B is the number of individuals born. D is the number of individuals that die. I is the number of individuals coming in via immigration. E is the number of individuals leaving via emigration. So, what's the take home from this model in its generality? Well, if birth and immigration is greater than death and emigration, what's the population going to do? It's going to grow. And then if birth and immigration is less than emigration and death, what's the population going to do? It's going to decrease. What if they're the same? A population is going to stay stable. All right. So, when we look around the world, we notice something about populations. They all have the capacity for exponential growth. Do they grow that way? No. They don't. But they have the capacity to do so. Here's an example. Bacteria are some of the fastest growing things in the world. There are certain bacteria that have the potential to divide and replicate themselves every 20 minutes. That's pretty impressive. At that rate of growth, unchecked, 36 hours later, you would cover the entire planet 1 foot deep in bacteria. Are you glad that exponential growth does not occur all the time? Because that's what it would look like, right? All right. So, in an unlimited environment, if there are no restrictions on the ability of an organism to grab energy, convert it into growth and reproduction, it's going to end up in a graphical plot that looks like this. 2 to 4, 4 to 8, 8, 16, 16, 32, on and on, right? And it will generate this L-shaped curve. So here's the assumptions of it. If the number of new individuals added per individual per unit time in the population is constant, right? And if the environment is constant, and the resources are unlimited, that's the kind of growth curve you'll generate. Positive rates of increase lead to exponential growth. Next time we meet, I'm going to show you a mathematical construct of measuring that, okay? Have a nice day. Okay, guys, we'll see you tomorrow.